Let's dive right into this explainer and uncover the secret, high-octane life of the world's absolute most famous element, oxygen. I mean, we breathe it every single second without even a passing thought. But hiding just beneath that invisible gas is this shape-shifting powerhouse that literally drove humanity to the stars. Today's agenda covers some incredible ground. We're looking at the many faces of oxygen, extreme alter egos in solids, the lungs of a rocket, liquid oxygen and propellants, the chemistry of thrust, and finally, fueling the final frontier. Let's get right into it.
Section 1. The many faces of oxygen. Meet the element. To really understand its secret life, we first have to look at exactly how oxygen shapeshifts into completely different forms at the molecular level.
So the crucial point here is that oxygen doesn't just exist as that simple air we breathe. Elements can actually arrange their atoms in different ways to create totally unique physical forms. We call these structural alter egos allotropes. It's kind of like taking the exact same set of Lego bricks, but snapping them together into completely different shapes. Just look at this incredible cast of characters. We start with O1. That's atomic oxygen, a highly reactive free radical that, amazingly, makes up 96% of the oxygen in low Earth orbit. Then, of course, we have O2, the dioxygen we're breathing right now, and O3, which is ozone. But it gets so much weirder. There's O4, this strange dumbbell-like molecule discovered back in 2001, all the way up to O8, which is actually a dark red solid cluster.
Moving on to Section 2, extreme alter egos and solids, pushing the limits. Now let's explore what happens when we really push this element to its physical extremes. It's such a bizarre juxtaposition. On one hand, you've got O2. It's thermodynamically stable, it sustains biological life, and it makes up 21% of our atmosphere. But if you just add one extra oxygen atom, you get O3, ozone. Suddenly, it becomes unstable. It actively destroys lung tissue and rubber, and yet this exact same molecule sits high up in our stratosphere and literally protects our entire biosphere from mutagenic solar UV radiation. Wild, right?
And the extremes definitely don't stop there. What happens when we apply pressure? Well, if you compress oxygen to a staggering 96 gigapascals, which is nearly 1,000,000 times normal atmospheric pressure, by the way, it fundamentally transforms into a superconducting metal. At that point, it starts looking way less like a gas and much more like heavier elements, think tellurium or polonium.
Section 3. The lungs of a rocket. History of propulsion. Oxygen's most dramatic alter ego isn't actually found in a diamond anvil press. Let's zoom out to the macro scale and see how humanity harnessed this element to conquer the final frontier of space.
Tracing the history of rocketry, we see a massive leap in exactly how we use combustion. We started way back in the 13th century with Chinese solid gunpowder rockets. But the real game changer? That happened in 1926. That's when Robert Goddard realized that liquid propellants were the ultimate key to true aerospace power. That specific breakthrough paved the way for the V2 in World War II, the mighty Apollo program in 1969, and it brings us all the way to today's private space industry innovations from companies like SpaceX and Blue Origin.
But here's the massive engineering hurdle they all had to solve. Because there's literally no atmospheric air in space, rockets can't just breathe to burn their fuel the way your car engine does. Instead, they must carry their own oxidizer. This acts as their mechanical lungs to sustain the violent combustion of fuel in a complete vacuum.
Section 4. Liquid oxygen and propellants, the ultimate oxidizer. So we've seen oxygen as a gas and as a solid, but its liquid state is what truly powers modern spaceflight.
By drawing ambient air right into massive separation units, cooling it down and condensing the O2, we get LOX. That's liquid oxygen. It's this beautiful pale blue liquid, and incredibly, it's paramagnetic. That means a magnet will actually attract it. But to keep it in this liquid state, it has to be cryogenically stored at a freezing -183 degrees Celsius.
So, you might be wondering, why go through all the trouble of handling something so incredibly cold? Well, LOX is the absolute industry favorite because it packs massive oxidizing potential into a highly dense cryogenic footprint. Basically, you can carry a huge amount of oxygen in a relatively small tank. Plus, its versatile compatibility means it burns highly efficiently alongside almost any fuel, whether that's liquid hydrogen, kerosene, or methane. It delivers the massive thrust-to-weight ratios you absolutely need to escape Earth's gravity.
Section 5. The chemistry of thrust. Measuring performance. Let's dive into the math and the physical mechanics of this whole process. how do we actually measure the raw power and efficiency of these cryogenic engines?
The answer is specific impulse, or ISP for short. This is pretty much the holy grail metric for rocket engineers. You can think of it sort of like the miles per gallon for a rocket. It measures exactly how effectively the engine uses its propellant mass to produce thrust. Naturally, higher numbers mean greater efficiency, which ultimately translates to higher velocities and much larger payloads.
When paired with liquid hydrogen, the sheer power of liquid oxygen is staggering. Just consider the jump in performance based on the environment. A LOX and liquid hydrogen engine, like the Space Shuttle's famous RS-25 main engine, generates an impressive 366 seconds of specific impulse at sea level. But once it hits the vacuum of space, where the exhaust gases can fully expand without any atmospheric resistance, that efficiency absolutely rockets to 452 seconds.
But to actually achieve this incredible efficiency, the internal engine environment has to become this chaotic, highly controlled inferno. It pushes every single component to its absolute limit. You have turbopumps forcing the cryogenic propellants into the engine at over 100 times normal atmospheric pressure. Then, specially designed injectors atomize the liquids into superfine droplets just to ensure perfect mixing. And the combustion chamber itself, it has to withstand temperatures soaring over 3,000 degrees Celsius to maximize that energy output.
Section 6. Fueling the final frontier. Liquid hydrogen. Now, as powerful as LOX is, it's really only half of the equation. It needs a partner. And that brings us to the ultimate cryogenic fuel.
Synthesizing this perfect partner, liquid hydrogen, is an immense industrial challenge. It all starts with a process called steam methane reforming, which chemically strips hydrogen gas away from carbon and oxygen. Next, the gas is painstakingly purified through pressure swing absorption. And finally, to actually turn it into a dense rocket fuel, it undergoes these massive compression and expansion cycles. It's chilled down to a mind-boggling negative 253 degrees Celsius. I mean, we are creeping right up to the very edge of absolute here.
As we wrap up this explainer today, I really want to leave you pondering this incredible transformation. We've taken an invisible gas that we inhale constantly without a second thought, traced its bizarre structural alter egos, and seen exactly how engineers compress and freeze it to unlock the explosive power required to literally leave our planet. If the very air we breathe holds the hidden power to propel humanity to the stars, it really makes you wonder, what other everyday miracles are just hiding in plain sight, waiting for us to unlock their secrets?